My name is Skylar McCaw, and welcome to my Lab 4 video about oscillation. In this lab, I used Tracker to examine a video of a spring mass system and to extract X and Y position data of the mass. I then created a computer code to model this experiment and used the position data in that code to get an accurate model. I then compared the predicted and observed motions and graphed the changes in kinetic energy, gravitational potential energy, spring potential energy, and overall energy. There were several fundamental principles utilized in this lab, including Newton's second law and the energy principle. The velocity update equation as well as the position update equation are needed, and various forms of energy as well, including kinetic, gravitational potential, and spring potential. For the energy portion of this experiment, the system is considered to be the mass, the spring, and the Earth. So the total energy change should be equal to 0 because nothing is acting from outside the system. Here's the video of the experiment loaded into Tracker. The mass is 0.402 kilograms and the frame rate is 10.5. The calibration length of the spring is 0.7 meters. Using Tracker, I plotted the motion of the mass at the bottom of the spring and it produced the graph to the right as well as the data points at the bottom. Now that the data has been extracted from the video, it is time to use it in the computer code to create a model of this motion. I put the X and Y position data into a .csv file so I could load it into the code. Here's the code for the model. I edited various parts of it in order to fit it to this experiment. I first input the values I knew: the mass, the initial position, and the initial velocity, 0. I also put in the spring constant and the relaxed length of the spring, which I found using the period based off the Tracker graph and the equations shown. Next, I needed to edit the equations within the code to accurately predict the motion, starting off with L, L hat, and S. I set L equal to the ball's position minus the spring's position, L hat equal to the previously defined L divided by the magnitude of L, and S equal to the magnitude of L minus L naught. Now that these spring-related equations have been set, it is time to move on to the energy of the system as a whole. First, I set each type of energy equal to their respective equations. Kinetic is 1/2 mass times magnitude of velocity squared, gravitational potential energy is mass times gravity times y displacement, and spring potential energy is 1/2 times spring constant times s squared. I then set total energy equal to all the energies added up. Now it was time to enter the loop portion of the code. Within the loop, I set the force of gravity equal to mass times gravity times a vector with -1 in the y position. I also set the spring force equal to negative spring constant times S times L hat. And lastly, F net equal to F grav plus F spring. Then came the velocity and position update formulas. I set ball.vel equal to ball.vel plus F net over mass times delta t, and I set ball.pos equal to ball.pos plus ball.vel times delta t. The last bit of code that needed altering had to do with the energy principle again. I set the different energies equal to the same equations I had before, and the deltas of each energy is equal to that energy minus the initial of said energy. Lastly, I set delta E equal to the sum of all the delta energies. Now that the code is done, here is the final result. The spring follows the same path as the spring in the video does, and the chart graphs out the changes in different types of energy, as well as changes in X and Y position. Is the energy principle satisfied? Well, looking back at the equation and knowing the energy change for the whole system should be 0, the graph produced by the code does satisfy the energy principle. The various forms of energy fluctuate throughout the experiment, but the total energy, represented by the orange line, stays at 0. Here are the two graphs produced by the position versus time. Looking at these graphs, as well as the data itself, the oscillation periods predicted by each are slightly different. For the X position data, I got the average oscillation period to be 1.614 seconds, and for the Y position data, I got it to be 1.517 seconds. Looking at the two graphs, the X graph is closer to the experimental data, so the X oscillation period is most likely closer to the true oscillation period. That's all. Thanks for watching.